All right, here we go. I'm missing my mic. Whoa. What's wrong with me? All right, here we go. So according to the Weissenberg theory, if there are 4 electron domains in the valence shell of an atom, they will be arranged in A or N blank geometry. What did you think on that one? Tetrahedral is correct. Good job. Oh. Tetrahedral is the answer. All right. So, tetrahedral, we made the balloons. When you tied 4 of them together, they went into that weird structure, sort of 1 up, and then 3 were pushed a little bit lower. Does that sound familiar? Okay. That we're going to call that tetrahedral. We'll go over that more today. All right. Now, the molecular geometry of the SF2 molecule is blank. All right, so this one's a little bit harder, and we haven't talked about molecular geometry yet, but the way that you solve this isn't too hard. You have to draw the Lewis structure. So it was SF2. All right, connect them with at least one line. How many total valence electrons did I have? I had 20, right? It's a question you should very extremely easily be able to answer. Everyone in this room should be able to do that. We had 7, we had 7, we have 6. That equals what? 20. I'm going to complete the octet on the outside. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So far, how many have I used? 16, correct? Well, the lines are 2. And so I just complete the octet on the S, correct? We okay with that? All right, so now this is sort of tricky because you don't know the answer, but I heard some people by the wall get it right. So the electron domain would be the same as before. It's tetrahedral. This is not the answer. This is not the overall answer. The electron domain is tetrahedral because there's 1, 2, 3, 4 places where electrons reside. Who is okay with that? Okay. When we have tetrahedral, we have 4 electron domains, but we have 2 non-bonding domains. Then we end up with a structure that we call bent. The reason it is bent is because this structure right here that I drew, if 2 of them are not there, like we don't see them because they're non-bonding pairs of electrons, the only part we write in the molecular geometry would be this blue piece, and we would call this a bent structure. Okay? We haven't gone over that yet, but we will today. And both of those should be like level 1 or 2 questions out of 10 to answer. Raise your hands if that made sense. Okay. You should have already read those sections. Whether you have or not, that's up to you, I guess. So today, we're going to make sure we hammer in electron domains, which is not bad, and molecular geometry, which is a little bit more complicated. So as we go through this, think of the balloon activity that we did, and things will hopefully make sense. All right. These are the electron domain geometries for 2 through 6 electron domains around a central atom. That's kind of blurry to see. Let me make that a little bit bigger. These should look somewhat familiar. Because of why? Because this is the exact same structure your balloons make when you tie them together, which is pretty random that they match, but they do. And they do because of the same idea. Balloons occupy space and will orient themselves away from each other. They'll push against each other. All right? Just like pairs of electrons, they will push each other away. All right? Now, what you have to know is you have to know the general shape. And we started yesterday, at least with linear, correct? So you need to know if you have two electron domains, you have a linear electron domain geometry. Okay? You need to know if you have three, you have a trigonal planar electron domain geometry. Now the electron domains are a little bit easier to remember because they're always the same. Molecular geometries change just a little bit. All right, 4, you need to know, is this shape, and you need to know it's tetrahedral. Sorry, I didn't say trigonal planar up here, but these are things you have to know. All right? Then, if it's 5, we have 1 up, 1 down, and 3 around the middle. We call that trigonal bipyramidal. Trigonal means 3. Bipyramidal means you have 2 pyramids, essentially. One going up and one going down. And then 6 is a little bit confusing in the name, in my opinion. It's this structure, and it's called octahedral. And oct means 8, right? And it does make sense because the faces here, there are 8 sides to this structure, even though there's only 6 atoms. Yes, Island. All right, because you have 2 that go up and down, all right, but then 3 that went around the middle. The 3 that go around the middle are 120 degrees away from each other. The ones that go up and down, they're 90 degrees away from the balloons that went up and down. If I can, I don't know if I can get rid of one of these very easy. I can pop it, but then everyone will freak out. All right. Just plug your ears. We're big people, right? I just need. Do I have any sharp pencil? Okay, ready here. All right. So this is that exact structure. The knot's kind of messing it up, so it's not even here. But if you have 5, you'll literally have 2 balloons that go up and down, and then 3 that orient themselves around the middle. So the 120s are from here to there, and the 90s are from here to there. Does that make sense? You okay with that? Like, you drew it, all right? And that's trigonal, bipyramidal. The pyramid, it has the 3 points and then the top, and it has it on the bottom. So bipyramidal, 2 pyramids. Okay? The trigonal comes from the 3 around the center. Now, wherever we rotate these, they stay the same structure. Remember yesterday, I don't know, was it Jansen, you were fired up how I drew my balloons sideways? Yeah? Well, we don't care what direction they point. They maintain pretty much the same structure. All right. Easy enough so far? Okay, this section, there is a lot of just memorizing. All right? So all one must do is count the number of electron domains in the Lewis structure, and the geometry will be that which corresponds to the number of electron domains. So this Lewis structure, so this is how we determine the electron domain geometry. We draw the structure like we had NH3 here. We had 1, 2, 3, and then 4. Okay with that? Go ahead. Yep. I'm going to go back for a second. Right here. Okay. Now, by the way, when you drew these shapes and I said put them here, it looks like Allison's got it. Like, you already have these drawn. Those were your balloons. Okay? You can take your notes about those next to those if you feel like it. You leaving town? Hold on. Pause this. So we're going to have a C, an H, and H. And a double bond here. So, how many electron domains? Tell your partner. For this carbon, 3 of them, right? This carbon, how many? 3 of them. So both of these have 3 electron domains, which means they would have what electron domain geometry? Trigonal. Whoops, that's whatever. Planar. Trigonal, planar. Okay? This seems like a weird and maybe not important thing, but for tests, both mine and the AP test, this is an important skill to possess. Do I what? Still can't hear you, I'm sorry. Flashcards, and then there's this like game website that I sent kids to last year. It's called Sparkle or something like that. Let's see, where's it at? It's on a slide forever here, right there. But this is the molecular geometry. So we'll get there, but you know, a kid came to B time yesterday and said, I need help memorizing my vocabulary terms. I don't know how to help someone memorize in B time. Just flashcards and practice, and they'll come pretty quick. I mean, some of them are easy. This one's not hard. This one's a triangle, so that might not be hard. If you've played Tetris, you know tetra means 4, so maybe that's not very hard. And then, so these two might be the weirder ones that are harder, but anyway. Now, this process of finding the electron domains is important and leads us to what is the more important topic, which is the molecular geometry. Okay, so comes from the electron domain geometry. The only difference, if you'll look, is that the molecular geometry does not show the non-bonding pairs, but it shows evidence of the non-bonding pairs. Because if you think about it, there's 3 things around a central atom here, right? So this should be just straight up trigonal planar. But this is not trigonal planar because these are bent down. Can you see that? So there had to be something to force them away, and they were forced away because this was a tetrahedral electron-domain geometry, and this pair, which we don't draw in the molecular geometry, pushes these 4 away. Okay? So the main difference between electron-domain geometry and molecular geometry is the electrons, you account for every electron in the diagram. Molecular, you only draw bonding electrons. But you will see them, you will see evidence of them. So, with each electron domain then, there might be more than one molecular geometry. And this is where that question answer comes from at the start. And I really, really want to encourage you to actually read the textbook and look through these, because it does help to understand these. All right, so here we go. If we have tetrahedral electron geometry or domain geometry, we can have 3 different types of molecular geometries. We can have trigonal pyramidal. The difference between trigonal pyramidal and planar is that these are bent away from just being. So it's still three things. So that's where the trigonal comes from. But since it's bent or nonlinear, we call it pyramidal. All right. The other option is when we have two non-bonding pairs. Then we just have these two hanging out. And two things around a central atom should be linear in our minds, right? But it's not. These are bent towards each other by the two other bonding domains that are not drawn, but are definitely there. Okay? So there's a chart coming up that you can add to the thing that you've already been writing. So linear is the easiest one. In this domain, there is only one molecular geometry, and that is linear. So the reason why is here in this note. If there are only two atoms in the molecule will be linear no matter what the electron domain is. And so if we only have linear, we have two things around the central atom, or just one thing around the central atom, and it's still just a linear compound. So the number of electron domains, if it's 2, the bonding domain is 2, there are no non-bondings, and you always have linear molecules. Okay? And then we'll step up the complicated problems pretty quickly here. Okay. Now, here we have trigonal planar, or we have 3 electron domains. So to do well in this chapter, you have to know how to find the number of electron domains from the Lewis structure. I think we're okay with that. You need to know what the domain geometry would be, and then we continue on here. If you have 3 bonding domains, and all of them bond to another atom, then it just matches. Okay, you have trigonal planar, you have trigonal planar. But now, if you have 3 electron domains, but 2 of them are bonding, and 1 of them is non-bonding, we call this bent as well, because it should just be here to here to here, but this pair is squeezing them closer together, or bending the straight line. Okay? Now, this bent and the other bent are slightly different. The difference is the angle here. The angle of this bent is 120 degrees. The other one is 109.5. The reason why is because the other one, it had another domain here and squeezed them closer. And that came from tetrahedral, which is on the next slide. Okay? Well, we'll get there soon. Non-bonding pairs and bond angle. Non-bonding pairs are physically larger than bonding pairs because they are not attracted to multiple nuclei. Therefore, their repulsions are greater. This tends to decrease bond angles in a molecule. This is a minute detail that you don't have to write down. But just know the more non-bonding, the tighter the angle. Are you okay with that? Like, tell me when to stop. Okay. Hold on. All right. Then a double or triple bond places greater electron density on one side of the central atom. Therefore, they also affect bond angles. AP used to care a ton about these bond angles, but they don't necessarily anymore. So just know non-bonding or double or triple bonds will squeeze things more than just single bonds. But you don't have to have those bond angles memorized. I'm going to get even lazier and put my feet up. Our attendance in this class is dwindling. It's annoying because marking attendance is hard. All right, I'm moving on. All right, tetrahedral. Tetrahedral, the number of electron domains is 4. All right. If they're all bonding, then your structure is the same as your electron domain geometry. Okay, that's true for all of them. If everything is bonded, then you're going to match the electron domain. Now, we still have 4 here. 3 plus 1 is 4. But if you have 3 bonding and 1 non-bonding pair, like here, we call that trigonal pyramidal. Trigonal because there's 3 atoms coming out. Pyramidal because the non-bonding pair force them to bend away and to make a pyramid. All right, we talked about this one twice already today. But if we have 4 electron domains, but 2 form bonds and 2 are non-bonding, we end up with a bent molecule like water. Because probably in science you've seen teachers write water this way a lot, or at least I have, right? Instead of just H-O-H. Well, the reason why we drew it this way is because there was 2 pairs of electrons here that pushed the H's away or forced the H's closer together. So that's why typically when I drew water, I drew it as it was bent, because it is bent. All right, we've probably never talked about these, maybe we have, but the dashes and the wedge, that's showing you perspective. You can look at it either way. The wedge is coming at you and the dash is going away from you, or vice versa. It doesn't matter. So what you need to know from this slide are these 3 structures that can come from 4 electron domains: tetrahedral, trigonal pyramidal, and bent. Okay. This is going well. Got 6 kids absent and 4 kids asleep. Lit. All right. Next, this little nugget is pretty important to understand what we're going to talk about. Trigonal bipyramidal electron domain. So now this is where we have 5. The first thing you need to know, there are 2 distinct positions in this geometry: axial and equatorial. Knowing these terms will help you. All right, the equatorial are the ones that go around. Okay, so between the 3, those are your equatorial bonds. And your axial are the things that go up and down. Now, if you understand how our planet works, that's not too hard to memorize. The axis goes up and down and the equator goes around. Okay? The reason why this will matter will be apparent on the next couple of slides. The name of the Earth would have come way before this would have. like the axis and equator. This stuff's like within 100 years old. Uh-huh. All right. So what you need to know here is that lower energy conformations result from having non-bonding electron pairs in equatorial rather than axial positions in this geometry. Okay. So what this is saying, we said a minute ago, well, that wasn't supposed to draw it in touch, that non-bonding pairs of electrons push away more than bonding pairs, right? So if we have a non-bonding pair in trigonal bipyramidal, it's going to go around the equatorial here, because then it only messes with things that are at 120 degrees, all right, and 90 degrees twice. If you put it here, it messes with the 90 degrees 3 different times, and that is not the favored, like, low energy structure of this. So non-bonding pairs go around the central atom equatorially in trigonal bipyramidal. So we're going to do that quick here. So when we have 5, if we have trigonal bipyramidal, if all of them are bonding, then we have trigonal bipyramidal. If we have a 4-to-1, we have what we call a seesaw. It's a seesaw because if you take this thing and you put it down, you'd have 2 legs, and then you'd have the 2 things for people to sit on. Okay? I took a picture because they actually did this one, if I remember right. I think this was Liam's. Hold on. If it's 3 and 2, we call it T-shaped, because remember the non-bondings go around the equatorial, and we're left with this structure, which right there doesn't look like a T, but if I rotate it, it looks like a T. T-shaped. All right, and then 2 and 3, this is pretty rare but pretty cool. They all go equatorial, so then you just end up with a linear, even though you had stuff everywhere. Okay. I know this. Will I what? Sure. All right. This one's typically the hardest of them. All right. The octahedral only has 3. Oh my. I thought I told the long enough story. So, octahedral, there's only 3. All right. If we have 6 and 6, we have octahedral and octahedral. If we have 5 and 1, we have what we call a square pyramidal. Square pyramidal, all right, one of them comes down here, and really, it's kind of weird, but they could be anywhere. Everything here is the same angle, even though it might not look like it is. So you plug one in, you have a square, like right here. You okay with that? But they're going to be pushed away from the blue, so that makes them somewhat pyramidal. All right, and then we have square planar, when my 2 non-bondings come up here. And so it's still square, 4 sides, but this time it's planar because there's nothing pushing one side away harder than the other. Diane, what's so frustrating about these? I'm reading your body language. Answering this question. You would solve it. You got to draw all three of them, find their electron domains, find the number of bonding and non-bonding, and then check your notes that you just wrote. Okay? Give that a try for the next few minutes.